Good afternoon, everyone. My name is Deka, and I'm a first-year PhD student at National Center for Nuclear Research in Warsaw. And I'm working on CMB weak lensing mainly. And in this talk, I'll discuss about galactic foreground bias in the lensing reconstruction. So in this conference, we have had a lot of talks about weak lensing. So I'll just skip over the introduction, but I'll discuss some important points here. So we all know about the CMB lensing. It's just the remapping of the primordial anisotropies. So this remapping happens by deflecting the photons that travels to us. And this deflection is done by the intervening mass distribution of the universe. And this deflection angle depends on the gradient of a quantity called the lensing potential. So this lensing potential is integrated effect of the potential that the photons encounter during its journey. And so here you can see that it's integrated along the line of sight. And so we can use this quantity. If we reconstruct this quantity, then we can use it to understand the mass distribution of the universe, and we can study the large-scale structures. And this lensing potential has angular power spectrum, which peaks at around degree scale. So and the distribution of this lensing potential is it's like a Gaussian random distribution. So what effects do we see because of lensing in the angular power spectrum is that lensing smooths out the peaks in the angular power spectrum, and so because of this smoothing, the estimation we do for the cosmological parameters that might get affected. So it is very important to reconstruct this lensing potential and subtract the bias from the angular power spectrum. Here is an example. So this is an exaggerated example. Here you can see in the top panel is I can use that pointer. In the top panel, this is an unlensed temperature map, CMB map, and this is an unlensed CMB polarization map, and this is the E mode polarization map. And here is a Gaussian potential Gaussian map of a lensing potential phi. And if we process these maps with this lensing potential, we get this kind of distortion. So what is important here is that this is a B mode polarization map, which is generated by lensing from the primordial E mode. So this is also an interesting thing of lensing, that it generates B modes from the primordial E mode. So it's important to subtract this lensing B modes in order to study the primordial B modes, right? So that's what I am working on actually. So our goal is to correctly reconstruct this lensing potential, and so we use a quadratic estimator to reconstruct this lensing potential, and this quadratic estimator is obtained by taking a quadratic pair of the temperature or the polarization fields. So if we take this quadratic pair and average it over an ensemble of multiple realization of CMB for a fixed realization of lensing potential, we get an estimate of this lensing potential. But the thing is, we cannot use this estimate directly to reconstruct the lensing potential, because the lensing potential is also a Gaussian has a Gaussian distribution. So if we and also it's statistically isotropic. So if we use this estimate and if we average over multiple realization of lensing potential, then we get average zero lensing potential signal. So what we do is this is a quadratic estimator defined by Okamoto and Wu in around 2002, and this is basically a weighted combination of this temperature and polarization fields. So this X here, you can replace it with either T, E, or B. So any combination of pairs you can use. And this D alpha is called the automaton quadratic estimator. So this is what we use in this analysis. And to estimate the power spectra of the lensing potential, we take such quadratic Okamoto and Hu quadratic estimator, and we contract them with each other, and we get the lensing power spectrum. But we also get a reconstruction bias along with it, because there will be some disconnected components, disconnected parts in the contraction here. So and if you look in the equations, we have a quadratic pair here. So when we contract them with each other, we'll get a 4-point correlation function. So these quadratic estimators are essentially 4-point correlation function. So we have to estimate the 4-point correlation function of these maps. And here's a plot of this reconstruction bias for an experiment that has the noise properties like Planck. Here you can see different estimators. So as I said, that we can take any combination of maps for this reconstruction. So if you take temperature map, it will be the TT estimator, or TE or EB. So these are those different estimators shown here. So for Planck, we see that the temperature estimator, the temperature estimator, the TT estimator, has the lowest reconstruction noise. And this gray line is basically the minimum variance combinations of all these estimators. But we'll focus on the lowest HL estimator, which is the TT estimator here. So I remind you that this is for the Planck. This is for experiments like Planck with that kind of noise properties. And for our analysis, we simulate some unlensed and lensed maps. And here is an example of that. This is a cutout of an unlensed map, and we use lensing potential generated from CMB with a cosmology that agrees with the Planck 2018 results. So this is a lensed map generated using that. So visually, if you see here, you cannot see much difference, right? But if you subtract the maps, you get some residuals, which is due to lensing. And this patterns actually has some correlation with the gradient of the lensing potential phi that we use to lens this map. So this is just the interesting thing to see. And the study I did is aimed at the CMB S4 survey, because we all listened to the talks in this conference that upcoming surveys will be targeting this weak lensing effect, and also they will target the E and B mode polarizations. So in this study, I use mostly the noise properties of CMB S4. And we all know that CMB S4 is a next generation CMB experiment, and it will have observations from two observation sites. One is from South Pole and one is from Chile, Atacama Desert. And this CMB S4 survey, they target both large scales and small scales structures in CMB polarization. So in our analysis, we are going to use isotropic Gaussian noise with the specifications of the large aperture telescopes of CMB S4, because CMB S4 also has small aperture telescopes, but here I'm mostly using this large aperture telescopes specifications, because I'm interested in the small scale signals of CMB polarization. So this is like 1.5 arc-minute FWHM, and the noise leveling temperature I use as 2.0 microkelvin arc-minute. And for polarization, you can just multiply the noise level of temperature with √2. So this is the noise property I use, and with this noise property, I use this Hu quadratic estimator, Okamoto and Hu quadratic estimator that I mentioned, and this is the reconstruction noise for this specification we use. So here you can see that the lowest reconstruction noise is is for the EB estimator, which is a polarization based estimator, right? So compared to Planck, this is a different result, because in Planck we had the TT estimator, which has the lowest reconstruction bias. So this means that for CMB-S4, the polarization maps will be important in reconstructing the lensing potential. And here I show the reconstruction of reconstructed potential power spectra, lensing potential power spectra. So for EB estimator, this blue line is the reconstructed power spectra for one realization. So that's why it has some cosmic variance. So and this black line is the theoretical lensing power spectra that we use to lens all those simulated maps. And this orange line here is the N0 bias. So and this color. So yeah, so this green line is the N1 bias. So by N0 and N1, I mean, so there in this contraction we did for this quantitative estimator, there are like different order bias. So this N0 bias is the most dominant one in the reconstruction noise. And this higher order N1 or NP bias, they are very small compared to this N0 bias. So we add up this theoretical power spectra, this N0 bias, and this green N1 bias, and we get an agreement with the reconstructed lensing power spectra. Okay, and here is a reconstructed map of the lensing potential. This is the input lensing potential map, and this is the one we reconstructed from the EB maps, using the EB maps. So yeah, this map basically has the power spectrum that is shown here in blue. Okay, and you can see that it reconstructs the input lensing potential to a certain extent, but it still have some bias. But all this analysis has been done without foregrounds. Now, in real life, we have this foreground contamination. I'm not gonna explain this slide because it has been already done by Artem. So galactic foregrounds has this different components which has different intensity at different frequency levels. And also, this plot also has been shown by the previous talk. So I'll skip to this plot, which is very important for my case. So here in the x-axis we have the multipoles, which basically represents the scales, and here we have the signal of this signal in terms of like angular power spectrum. And you can see here that for E modes, the E mode signal dominates over the foreground bias at smaller scales, which is the higher multipoles. And here we can see the lensing B modes, and you can see that this lensing B modes is completely dominated by the noise, right? So it is very important to study the effect of foreground in the lensing reconstruction, because we are using the polarization based maps to reconstruct this lensing potential. And in this gray lines actually show the primordial B modes, which has very small signal, and these are for different tensor to scalar ratio. So if we want to probe this primordial B mode, we must reconstruct this lensing B mode and subtract them. But before reconstructing the lensing B modes, we have to first take care of this foreground bias, right? Okay, so here I show again the reconstruction noise, but this is when I add the foreground to the simulated maps, right? And here you can see that this reconstruction noise drastically changed, like for some estimators, but for some estimator it doesn't change much, right? So for EB estimator, let's check for EB estimator, because that was the estimator that has the lowest noise for CMB-S4. So for EB estimator, this reconstruction bias with after adding the foreground changes very drastically. It goes very up. So now the EB estimator is no more the lowest reconstruction bias estimator. And if you look at the EE estimator, which is the green one here, so the solid line is without foregrounds and the dashed line is with foregrounds. So for EE estimator, the reconstruction noise doesn't change much. That means this foreground doesn't have much effect on the EE estimator. One important thing to note here is that I used 80% sky fraction of the sky, and I used a 20% mask to mask this galactic plane. But when we want to reconstruct this lensing potential, we want to use as much of the sky as we can. So for that, we'll have to do component separations. But right now, all these results are without component separations. That's why we see a lot of high increase in this reconstruction bias. In this plot, I show you the effect of masking. So here, this solid line is for a mask which we use like 50% of the sky. So all the galactic plane and the foreground component is masked here. And this dashed line is the reconstruction noise for this mask, which is plus 20% of the galactic plane. So you can see some of the foregrounds are still there, so they will affect the reconstruction noise. So that's why this reconstruction noise is high for this mask, and it gets low, very low, and this looks like as if we don't have foreground at all, right? It goes back to the original level almost. So masking is an option, but we want to use a higher percentage of the sky when we reconstruct this lensing potential. And also for CMB-S4, the sky fraction that CMB-S4 will observe will be closer to galactic plane, somewhat here. So it's important to understand this foreground bias and subtract them in the lensing reconstruction. Okay, so here is a reconstructed lensing power spectra from our simulated maps, and these results are for with foregrounds, and this one is for EE estimator. So in the reconstruction noise panel here, we saw that this for EE estimator the reconstruction noise doesn't change much. So that's why the reconstructed lensing power spectra actually agrees with the theoretical expectation of the sum of this actual lensing power spectra and the noise, right? And here is also this blue line shows the reconstructed power spectra, but here we added this black line, which is the fiducial, the theoretical lensing power spectra, and this N0 bias, which is this orange line, and in theory they should match if we do not have any bias except the reconstruction bias, right? But here you can see some positive bias here when we reconstruct this lensing potential. So what is this bias, and where is this coming from? So we have to understand that, and this bias comes from another term that has not been included in the reconstruction. So when we are taking the estimates and taking average of them, we're including the foreground power as well in the maps, because we are not doing foreground component separation. So when we do this reconstruction with this quadratic estimate, there's another bias term that arises out of this, which is, so this f hat is quadratic estimate of the foreground maps, and this N0 bias is similar to the N0 bias I showed earlier, but we only use the foreground power spectra to compute this N0 bias. So the difference between these two terms is still called here F as systematic, and this is still there in the reconstructed signal. So this is like this has been discussed in our previous paper as well. So we wanted to check if this is true, that this FL systematic is the bias which is causing this extra positive bias here, right? So to test that, we calculated this FL systematic for 80% of the sky, 80% fraction of the sky, and this red line is smooth, like moving average of this FL systematic bias, and we add this to the previous plot. So here we only added these two terms, the black line and the orange line, and we got a bias. Now we add this FL systematic as well here. So now this theoretical estimate actually agrees with the reconstructed lensing power spectrum from our simulations. And so in summary, this the polarization field estimators are important for CMB like experiments, but the foreground contamination is huge in this map. So we need to do component separation to reduce this FL systematic bias, and after component separation, we also have to study the residual bias in this lensing reconstruction. So yeah, thank you.